Okay, calibration frames. If you're an amateur astrophotographer, especially if you're a beginner, they are the bane of your existence. At least they've been the bane of my existence in astrophotography since I started, and even now sometimes calibration frames, they give me headaches, right? I don't know about you, let me know, but yeah, for me it's been sometimes an issue. And I've done multiple videos, especially one recently where I show you which calibration frames you need to take and how to take those calibration frames depending on your situation, whether you're using a cooled astrophotography camera, a DSLR, specific models, etc. I'll put the link to that video up above, also down in the description. But today I want to go more into the theory of the calibration frames, so flat frames, bias frames, dark frames, and dark flats, how they work together to and what effect they actually have, as well as some misconceptions or some mistakes to avoid when you're using those calibration frames, especially if you're using the full set of all those 4 types of calibration frames. So fasten your seatbelts, we're gonna get geeky. But first, let's look at a very interesting chart about calibration. That chart was made by one of my Patreon supporters, Ray Latoul, and I think he did a great job. And I want to use that chart to go through those potential mistakes, misconceptions, as well as what things actually do. So this is a chart, visual chart of astrophotography calibration. Let's start here at the very top with the light frames. The light frames are simply your raw frames without any processing or debayering or anything done to them that you took of your target. So you were imaging, let's say, the Andromeda Galaxy M31. You took 100 exposures of 120 seconds each, and those are your light frames. You haven't done anything to them. They are the raw output of the camera. And those light frames, they contain a certain number of sources of noise. The largest one typically, especially for people like me who live in light polluted areas, like Tokyo for me, is usually the light pollution, and specifically the random element of light pollution, which is called the light pollution shot noise. And you can see that this is what is called in this particular chart the random noise, or at least part of the random noise, because there's some more random noise from like the actual image that you're taking. There's some from light pollution, but there's also some random noise from your target itself, because the target, it might emit on average, let's say for a given area you're imaging, I don't know, 20 photons per second, but maybe 1 second it will be 17 photons, and the next one 25, and then afterwards 22, and then afterwards 18. It's just on average it's 20, but in a given exposure, from one to the next, you're not going to get exactly the same number of photons from that target, and that variability is the target shot noise. Then we have noise that comes from your camera tech itself, from your sensor, which is the thermal noise and the read noise. The thermal noise is simply because our camera sensors, they're a bit dumb. They mistake heat for light, or more specifically, like what they do is normally they take photons, convert them into electrons, but heat is also very annoying, is that it can basically cause electrons to also appear in pixels. So pixels will be like letting photons fall onto them. Those photons convert into electrons effectively, but heat from your sensor at the same time will have like some electrons also being generated because of that heat for no reason. So that's the thermal noise, also known as the dark current noise, and it's typically a function of temperature of your sensor as well as time. Like the longer you expose, the more of those random heat-related electrons get stored into your pixels. So that's thermal noise. It comes from the electronics under the sensor, and your sensor heats up while it's exposing. By the way, there's a misconception there that you can avoid a lot of that issue with uncooled cameras like DSLRs by taking short exposures. That actually doesn't really work, because if you're taking many short exposures in a row, the sensor will heat up anyway, and it does not have the time to cool down between exposures. So the thermal noise is going to be the same impact for the same total amount of imaging time, regardless of whether you took long exposures or short exposures on a cooled or uncooled camera sensor. So that's thermal noise. And then we have read noise. And read noise, it's also from your camera tech, let's say you finished your 120 seconds exposure on your target, and so each pixel is very happy, it has its electrons in there. It's just that now we need to read out how many of those electrons there are. And the problem is that when we read those electrons out, we have to empty our pixel. So we empty the pixel, and as we empty it, we count the electrons. But unfortunately, our counting tools, they're not that precise. They can miss electrons, or they can overcount electrons. And because while they're reading the pixel, they're emptying it, it's not like they can actually measure multiple times the same pixel and then average things out to avoid the read noise altogether. They have to do it in one go, and so there's error there. And that error, let's say you had 10 electrons in your pixel, but you measure only 8, that's your read noise, that difference. And that's random, and it happens per exposure, right? So it's every single exposure you include a tax in terms of noise, which is the read noise. And then we have another element here, which is the optical noise. And optical noise, I don't know if the term is scientifically correct, but it's basically to denote the issues caused by your optics. So your optics will cause issues like vignetting, and if you have like dust motes on your filter, on your camera sensor, you might get donuts or circles, like discs of darker areas on your image, and depending on your telescope design. And yeah, that's part of what we can have as part of like optical noise. You could even consider like the fact that stars are not pinpoint, they're actually slightly larger in a way as optical noise. That's getting into the weeds. But that optical noise, when it comes to vignetting, and when the corner of your image it's darker, or when it comes to those dust motes, they can be fixed via calibration. So we have all of those sources of noise, and calibration will help, not remove, but will help a bit with each of those sources of noise. And of course, in those light frames, we have the target signal, right? The target photons. Okay, so then we get, so we have light frames, and now we go to the calibration frames. We have the dark frames for the light frames. We have the flat frames. We have the dark frames for the flat frames. And then we have the bias frames. Let's get into each one after another. First, the dark frames for the light frames. Basically, if I took 120-second exposures throughout the nights, and let's say I was cooling my camera sensor to minus 10 degrees Celsius, absolute value, and I had like a gain of 100 and an offset of 50, something like that, right? The dark frames, they're taken with the dust cap on. You need to make sure that there are no light leaks whatsoever. You want to eliminate any impact that the optics or light could have. So it's really like no light whatsoever reaches the camera sensor. And you take an exposure with exactly the same settings, so minus 10 degrees, 100 gain, 50 offset, as your light frames, and of the same length as well, 120 seconds. And when you're doing that, because you're making sure that the sensor sees no light whatsoever, it will not collect any target photons. It will not collect any shot noise from light pollution or from the target itself. It will not collect any optical noise from your optics, because you cannot have shadows of dust motes and you cannot have vignetting without light, right? So it only gathers effectively a copy of the thermal noise from your lights and of the read noise from your lights, right? So you get a copy, but when I say copy, it's kind of a randomized copy, or like the average, a randomized copy. So each of those dark frames, it will have a certain amount of thermal noise, a certain amount of read noise, but just like I explained earlier for shot noise, there's a random element to thermal noise and to read noise. So I gave an example earlier of read noise, like my pixel had 10 electrons, but I only counted 8. That's read noise. And the read noise is effectively a standard deviation in statistics. So if my read noise is 3 electrons per pixel, it means that effectively, when I count my pixel that has 10 electrons in it, I have a 66% chance of counting between 13 and 7 electrons instead of the ideal value 10, right? We can be even less precise. We have a 95% chance of being between 16 and 4 electrons, like a wider range, but like most of our measurements will be between those two values. For small values of signal, like the 10 electrons was the signal we were trying to measure, that can have a huge impact. If my pixel contained like 1,000 electrons, then the value 95% of the time we would be measuring between 1006 and 994. It's not such a big deal, right? It's much less of an issue compared to the value we're actually trying to get. So you can see read noise can definitely impact the measurement of pixels that have very low values. And that actually impacts the dynamic range. But anyway, we have the same thing actually with thermal noise. There's a random element to it. So each dark frame is trying its best to reproduce the thermal noise and the read noise from your light frames, but it's never a one-to-one. So that's something to keep in mind. Okay, then we have the flat frames. So flat frames, they're basically trying to characterize your optics by giving us an idea of the vignetting introduced by your optics, as well as any dust motes, that kind of stuff. So for that, you take a flat panel, a t-shirt, etc. You basically want to point your telescope at a perfectly flat field of light and then measure what it looks like on the sensor. Because then you'll have like the shadow of the dust motes, you'll have the vignetting from your optics, but you will not get anything from the target, right? Because it's a perfectly flat white field or anything like that. So you do get, in that case, optical noise, but also some thermal noise and definitely read noise, right? Because the flat frames, they're typically short, can be very short. Typically, I have mine like roughly 1 second long. For some cameras, you want them 3 seconds long. For a lot of cameras, you can be sub-second without any issue. So the thermal noise would actually be very, very small for flat frames. Not a big deal. But the read noise, it's just as high as ever. Fortunately, the flat frames, the value we get is roughly 1/3 of the total amount of electrons that each pixel is able to count. So the read noise doesn't have such a huge impact on the flat frame itself, but it could have on the actual correction of your light frames with flat frames. We'll get that in a bit of a moment. Okay, and then we have dark frames for flat frames. As we said, flat frames, they have thermal noise and they have read noise, right? Just like light frames have thermal noise and read noise. How can we get rid of thermal noise and read noise? Well, we can take dark frames for flats, which would need to have exactly the same parameters as the flat frame. So the same temperature, exposure length, gain, offset, if it's a DSLR, ISO, that kind of stuff. So it's kind of like a dark frame, but just for your flat frames. Okay, so with that, technically, if we have all of those, especially if you have a lot of darks for lights and a lot of darks for flats, then that's enough to basically calibrate all of those sources of noise. The optical noise, the thermal noise, the read noise. Random noise, there's not much we can do about it via calibration. But it's easy to actually take bias frames, which are very short exposures, typically the shortest that your camera can manage. And you take those bias frames just like you take dark frames in complete darkness. So you won't get any noise from your target, no noise from light pollution or light leaks if you take your bias properly, which is super important. You won't get any thermal noise because the exposures are so short. You just get the read noise from your bias frames. And just like the others, this is an evaluation of the read noise. And what's going to be very interesting is that when you have the full set of calibration frames, like we do have here, the bias frames will be used to correct the read noise from your dark flats here, from your flats there, from your dark for lights there, and from your light frames, right? So it's super important, and this is where there's a common misconception, which is like, oh, I can take just like 20 bias frames, or even something like that, right? But if you have the exact same amount of bias frames, as you do like darks and dark flats, then those bias frames are completely useless. Because what you could do is, if I want to remove the thermal noise and the read noise from my lights, I can just use darks for lights here. And I already have 20 of those. So by taking all of those dark for lights and averaging them out, I will have a good estimation of the average thermal noise in my light frames, as well as a good estimation of the average read noise from my light frames. And so I can remove the average thermal noise and the average read noise from the lights very accurately with just this. If I'm using bias frames where I only have like 10, let's say, the bias frames will give me a less good estimate of the average of the read noise of my sensor for the gain and offset that we have selected. And so when I use my bias frame to remove the read noise from the darks, I'll do it in a way that is not optimal. And so there might be a bit of average read noise left in the darks that will then be used with the lights. So that can be an issue. So you want to always have as many bias frames as you can. And yeah, 100 is typically a good idea so that you can have a real good bias calibration. Okay, so what happens next? We create the master bias. And by the master bias, it just means that we take all of those 100 bias frames, and per pixel, we'll do the average. So pixel 1 on frame 1 plus pixel 1 on frame 2 plus pixel 1 on frame 3, etc., plus pixel 1 on frame 100, add all of those values, divide by 100, you have the average value of pixel 1 across all of your bias frames. And then you do the same thing for pixel 2, 3, 4, blah, 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 and up all the way to, let's say, pixel 9 million if you have something like the 533 sensor, right? So yeah, it's a lot of averaging to do, but fortunately, your processing software will do that for you. And when you do that, you end up with a master bias, and the master bias contains an average of your read noise. So when you're going to take a master bias and basically subtract the average of the read noise from your light frame, you do not get rid at all of the random component of read noise, but you get rid of the average pedestal, or the average value that your sensor has at rest, kind of thing, which depends both on the read noise and on your offset, actually. So your master bias frame will help remove fixed patterns of read noise on your camera sensor. It will, however, leave the random component of read noise in your images. There's nothing you can do about that. So you take your master bias frame, which is a good average of the read noise value of your sensor for the gain and offset that you have used across all of those frames, and you take each dark flat, you subtract the master bias from it, pixel per pixel. So you take dark flat 1, pixel 1, minus the pixel 1 from my master bias. Then dark flat 2, pixel 1, minus the pixel 1 value from the master bias. Then you do that for pixel 1 for all of the dark flats, then for pixel 2 for all of the dark flats, etc., until you have subtracted pixel per pixel the value of the pixel from the master bias from each of the dark flats. And you'll do exactly the same thing for the flats, and then exactly the same thing for the normal darks, and then the exact same thing for your lights. So what's happening is that now all of your other calibration frames have been read noise corrected. And when we say read noise corrected, again, it does not mean that we have removed the random element of read noise, which is the thing that actually affects your dynamic range, for instance. But it does mean that we have removed the average amount of read noise as well as offset from the camera. And that's actually super important for your flats. Extremely super duper important. You cannot do flat calibration without either bias frames or darks for flats. You cannot. So it's something very important to note, and we'll understand why a bit later. Flat frames absolutely need to be read noise corrected. Okay, Let's remember that. But now we have, as I mentioned, basically we've removed the fixed pattern associated with your sensor, offset, and your average read noise from each of your other frames, from the light frames to the darks to the flat darks. Okay, great. Let's go next. Next, we can create a master dark for the flats. So we're going to take all of your flat darks that have been read noise calibrated and offset calibrated. You combine them into a master dark flat. So this is an average again, just like we did an average of the bias frames to get a master bias. We take an average of the dark flats to get the master dark flat. And this master dark flat will be used to calibrate the flats. So what's happening when you calibrate the flats themselves, if you look here, you had the flats still had like optical noise and thermal noise. They also still have the random aspect of read noise, but we're keeping this chart kind of simple. And by calibrating those flats with the master dark flats, one by one, you take each flat and pixel per pixel, you subtract the value of each of those respective pixels with the value that's in the master dark flat for that particular pixel. You get a flat that has the thermal noise corrected as well as the read noise corrected, right? So now the flats themselves should have a good representation of the optical noise. And to make sure that they do, because we're using a flat field which has light. Light is photons. So you have for every second, you have an average number of photons that falls onto each pixels, but from 1 second to the next, it might not be exactly the same number of photons. So you do have, even with flats, shot noise. So to basically remove the random component or basically mitigate the random component of that shot noise, you average out all of your flats together. So now you have your well-calibrated flat frames, and you put them all together, you stack them, and you average them out, so that now you're left with a very smooth version without much, if any, impact from shot noise, with very little impact from thermal noise, with no pattern or fixed pattern from the sensor read operations or thermal noise. You get some very clean master flat frames. And what's very important to note is that they also do not have a pedestal, like kind of a pedestal value that is created by the offset of your camera, for instance. Okay, so what happens next? Well, next we need to do exactly what we did for the flats, but for your light frames as well, right? So we're going to take your read noise or average read noise corrected dark frames and take them, all of them, average them into a master dark frame. And that master dark frame, the reason we average them out is that because the thermal noise has a random component, right? So we get the average of that random component. And that's what your master dark is, a representation of the average dark current noise in your sensor, at least for the exposure time, temperature, gain, and offset ISO of your sensor. So now that you have this basically master dark, which has a measurement of the average thermal noise for your conditions, then you can use that and subtract it from each of your light frames, so that the light frames have this average of the thermal noise removed from them. The random element of the thermal noise, just like the random element of the read noise, are still there. Don't make any mistake about that. But the fixed pattern related to the average of that thermal noise has been removed. So you have some quite clean light frames, but they still have, the optical noise, your dust motes and your vignetting, right? So we're going to do something about this. And that's basically the last step. We're going to take the master flat frame and we are going to correct the light frames with the master flat. And unlike previously when you were like calibrating your lights with the master dark Are you were calibrating your flats with the master dark flats? Are you were calibrating your darks or dark flats with the master bias? We were doing just subtractions, right? So something to note is that your offset on your camera, when you set an offset for your exposures or your camera settings, you typically don't have that in the ASI Air, but if you use Nina or StellarMate, etc., you do get to set a value of offset. This actually sets a minimum values for your pixels, like a pedestal there. And that's a constant. So basically, each value that the pixel measures will be the value from your target and the light pollution, etc., plus that offset in electrons. So we've added a constant to every single pixel, and that constant might not be exactly the same per pixel, but it's roughly the same. So that's the pedestal that I'm talking about. And when we're just doing subtractions, if your light frame and your dark frames are taken with the same offset, which is why it's very important, when you subtract the dark frame from the light frame, you subtract their offset at the same time, right? So the offset in each of those cancels itself out. But if you do a division, that's no longer the case. And that's what's happening here. Basically, you take your corrected light frames and you divide them with some normalization going on. Yeah, your light frames, dividing them by your master flats. So pixel 1 of calibrated light frame 1 divided by pixel 1 of your master flat, and then you do that for each of the light frames, and you do the same for pixel 2, pixel 3, etc., etc. If you have a pedestal that's remaining in your master flat, you're going to divide too much, and so you're going to overcorrect your optical noise. Basically, you will, if you had like the darkened corners due to vignetting, because you're overcorrecting, then you will have your corners that will be too bright next. So that's why the master flats and the flat frame calibration absolutely needs to be done with either dark flats or bias frames or both. And the main reason for that is that, sure, it's nice because it cleans up the flat frames a little bit, but they don't need cleaning up that much. The real main reason is to get rid of that pedestal. If you ever end up, by the way, with flat frames that are overcorrecting your light frames, you should be able to actually use a pixel math operation to take your master flat minus some small value constant. Then you try the calibration again, see if the corners are overcorrected still, and you keep increasing that subtracted number until you get the perfect flat frames for your image. But that's a huge amount of work. It's not worth it. Just calibrate your flat frames properly first. So there you go. Now you have your light frames that have been corrected for the optical noise. Again, probably not the right scientific way of calling that, but you now have your light frames. We've removed the average of the read noise plus offset. We've removed the average of the thermal noise, and we've removed the average of the optical noise as well, using this whole process there. And so now we're left here with basically your target photons as well as random noise. And that random noise is mostly shot noise from light pollution and shot noise from the target. That shot noise is when there's an average value per second of photons that fall onto your sensor from your target, from the light pollution. But from one exposure to the next, you're still not going to get the same value. You want to get that average value back, and for that you'll be taking your light frames that have been well calibrated and then average them all together so that we get much closer to the average value of what we were imaging, so that the shot noise is smoother and we can remove it via gradient removal, and you get a better view of your target. And that's basically it for this video, showing you how the calibration is done when you have the full set of calibration frames. When you don't have the full set of calibration frames, I typically don't. I usually have only the light frames, the bias frames, and the flat frames. But you'll note that because I have bias frames, I can probably remove properly remove the offset from the flat frames, so I can properly calibrate the light frames with the flat frames. And my bias frames, they basically contain the read noise, or the average of the read noise, so I can average out the read noise from my light frames. And I don't bother with the thermal noise because I cool my sensor down to a very low temperature, and at that temperature, even with my exposure length, it's not significant compared to the light pollution shot noise. So it doesn't really do anything for me. If I were to take images from much darker zones, I would probably take the pain of doing the dark frames as well. But so you can see that you can simplify that process, but it's very interesting to me to see visually, and I want to thank Ray Latoul for making this graph and sharing it like that, because it's really powerful to actually view and understand exactly how things work, and also make sure that we are aware of the limitations of what we're doing, because I often hear that calibration removes noise. It does, but not the random part of it, right? Something to remember. That's what the averaging will do, or will help to do to some extent. And we also understand why we want to have as many bias frames as possible, let's say 100 of them. We also understand why the flat frames absolutely need to be at least bias or dark flats calibrated, so that they don't have a pedestal, and so therefore the division of the light frames by the master dark doesn't get crazy because of the pedestal left over in the master flat, causing overcorrection. But I hope this was interesting to you guys. Maybe you learned something. But if you have any other misconceptions, corrections, tips and tricks you want to provide, please provide them in the comments. And if you've watched this video, know that I can and definitely do make mistakes. So I highly encourage you to check the comments out as well, because a lot of times you guys, you correct me, you help me get better, and you help everyone else watching the video and reading the comments really get even more details and background about everything. So please go ahead and check the comments. Add some comments yourself, like the video, it really helps out the channel. Thank you so much for watching till the end. By the way, that's a measure that YouTube looks at a lot. And if you want to support the channel even more and you're planning on buying anything from Agena, High Point Scientific, Amazon, etc., if you do so after clicking one of the links that I have down in the description, it will help me out at no cost to you. If you want to sponsor the channel directly, make those videos possible, you can become a channel member. That's the join button next to the subscribe button, or you can become a Patreon supporter. The link is down in the description. Some of my Patreon supporters have access to my videos early and without ads, as well as a Discord server. And you guys, you know it, I say it every single time, but you make all of this possible. So thank you so much for your support. Anyway, I hope this was useful. I hope I didn't make too many mistakes. Thank you, as always, so much for watching. Don't forget whenever you can to look up at the stars, and I'll see you next time.